So, good evening, and I am Shannon Cleveland. And today I'm going to present how resin selection and structure development has advanced film technology for bioprocessing. If my mouse works. There we go. I will review some background for the film, discuss fluid contact layer development, describe how the gas barrier layer was developed, share how we incorporated mesh into the film structure, review how we develop the tie layers for interlayer adhesion, and finally discuss the outcome in terms of film performance. Single-use films can be used throughout the unit operations of bioprocessing. Here I show the film being used in our Mobius bioreactors, flex-ready flow paths, mixers, storage systems, and transportation bins. And here we have our first poll question. What, if you were to develop a new film, would it be that you would prioritize? Would it be clarity, cell compatibility, and extractable leachable profiles, durability, or would it be gas permeability? And there is a poll slide here that if you see it on your screen, you might have to drag it over to be able to respond. So I'll give you a little time to put your input in as what you think would be the priority in developing a new film. I feel like it's a little jeopardy here. All right, and I think, so we'll just have a few moments and then we can share the results. All right, so most people think cell compatibility and extractable leachable profile and durability. All right. I think you did pretty good. All right, so there we go. When talking to our customers, durability can be a key factor. The average cost of just one leak can cost anywhere from $60,000 to $600,000, with the most costly leak occurring with transportation of bulk drug substances. Another area of concern is cell compatibility. Customers note variable cell growth that can change by film supplier and even between lots of the same film. A study published in the Journal of Pharmaceutical Science and Technology discovered that the antioxidant ergophos 168 degrades during gamma sterilization into 2,4-ditert-butylphenyl phosphate, and this chemical can negatively impact cell growth. So considering the last two slides, the primary objectives for the new film are to reduce or eliminate leaks by reimagining the film structure to increase durability of the film, and to reduce or eliminate compounds that are risky to cell growth by carefully choosing polymers which minimize extractable leachable profiles and maximize cell growth. That may sound simple, but there are many other performance criteria to consider when developing a new film. Some of these criteria are listed here. The new film designs need to robustly ensure quality performance for all design criteria. We had many tools to help us explore and measure success. To vet designs for technical feasibility, we used an in-house pilot scale 5-layer extruder laminator that I show here with my boss Dave saying hello here, that allowed us to screen resins and potential film designs. The trial film structures could be tested for physical performance. Shown here are some of those tests. Some film-based tests were abrasion, so we have the Tabor abrasion table pictured here. Flexibility, this is the Gelbo flex test. Tensile, so we had tensile strength and also tear strength. And we also looked at puncture. And so film in product testing was also done, including vibration and impact testing. And you can see impact down here. Trial film structures were also tested for cell growth compatibility. The cell growth in post-gamma film was benchmarked against cell growth in glass. Cells were incubated, prepped for culture, cultured, and then cell density and viability were evaluated. So let's review the structure development of the fluid contact layer. Our main objectives for the contact layer were to identify a resin without ergophos 168 and have a high cell growth compatibility. To use a resin that could be co-extruded and have a low extractable leachable profile and still provide robust seam strength. We chose to use a polyethylene resin for our contact layer due to its availability, stability, chemical compatibility, and its wide range of density and melt flow for processing. Polyethylene also has a history of providing robust seam strength. Within the polyethylene family, we explored new resin grades, blends, and thicknesses. We tested potential polyethylene candidates for cell growth compatibility. We used a film to fluid ratio that are 7 to 20 times higher than what's used in a typical customer application. So you can see here the bag that we used, and it had the fluid to the film to fluid ratio of 2 centimeters squared per 1 ml. With our selected polyethylene resin, we vastly improved viable cell density when compared to a polyethylene resin that contains ergophos 168 and met our target of closely mimicking cell growth in glass. And you can see on the graph here that the glass control sits right here in the blue line, and that close to out to day 5, what our viable cell density was, and that our polyethylene without the ergophos 168 closely mimics that, whereas the polyethylene with the ergophos 168 did not fare so well in terms of cell density. Now let's move on to review the structure of the gas barrier for the new film. Ethylene vinyl alcohols are commonly used as gas barrier layers and films, but they aren't known for their flexibility. With standard grades, low oxygen transmission resins have low flexibility, and more flexible grades of EVOH provide less of a gas barrier. And you can see that on the graph here, that low flex crack resistance really goes with the higher performing low oxygen transmission rate. But specialty grades break this trend by providing both a low gas permeability, relatively, and increased flexibility, and this is vastly increased. We put the resin grades of EVOH to the test. We used the Gelbo flex tester to simulate extreme handling. The Gelbo flex test repeatedly twists a film sample over 420 degrees, then crushes the sample. So this acts like a piston, and you take a flat sheet and you attach that flat sheet to this piston. And as the piston closes, it rotates that 420 degrees. And when it's done crushing it, it opens it back up and it pulls it back out, right? And you can cycle to however many cycles that you choose. And then to evaluate them, the samples are then flattened, and dye is used and squeegeed over the surface, and the holes and cracks are detected by the dye that penetrates through the flexed film. And here you can see that there are several circled areas where we had discovered cracks or pinholes by detecting dye on the opposite side in the paper. Extruded 5 mil EVOH films were evaluated post 200 Gelbo cycles. So we looked first at grade C, that middle of the road standard EVOH grade that was depicted in the graph a couple slides earlier. And it resulted in multiple large holes after flexing. And you can see all of the flex marks here and the stress, but some of them resulted in holes. And then we took grade A, which was the highest flexibility specialty EVOH grade on that graph. which robustly remained integral over the 100 samples that were flex tested. So you can still see that there are stress marks, but it remained integral over the dye test. So we had no leakage through this film over 100 samples. So this new specialty resin was selected and improved both gas barrier properties and flex durability. So now let's review how and why mesh was incorporated into the film structure. So why merge mesh with a film? The combination is known to increase durability and strength. Here are some industry examples of mesh film combinations. You have an airlift bag, which sometimes people use to lift up their car, blood pressure cuffs, and even the air dome structures. There were many types of mesh formats to explore. We looked at wovens, knits, non-wovens, apertured film, carbon fiber composites, and within each format, there were variables like material of construction, the fiber diameter, and the fiber density. There was also the question of where to best place the mesh. Should it be on the outside, buried, but above the gas barrier layer, or below the gas barrier layer? And so here's our second poll question. What structure do you think would be best to enhance the durability and strength? Would it be A, on the outside, or B, under, like above the tie layer, or would it be below the tie layer? I really do. I wish I had the little Jeopardy music. All right, let's see what everyone thinks. We have a tie between putting it above or below the barrier layer. All right, well, we'll see how that goes. All right. Many combinations were trialed to find out what kind of mesh and mesh placement would work best. Experimentation combined outer layer resin, tie resins, mesh type, mesh material, total and individual layer thicknesses, and even process conditions. Here are some graphical data showing abrasion, puncture, and tear performance versus a few of the trialed composite films. We found that nylon, I'm sorry.
Sorry.
Did I?
We're not seeing your screen. You were not seeing your presentation anymore.
Oh no, it like booted me out. All right.
Yes.
Sorry, I don't know what happened. I will share again.
All of a sudden it disappeared.
Okay. Yeah.
There it is.
You see now?
Yes.
Okay.
Okay, thanks.
I know my picture came up and I thought something was up. Okay, thank you. So I will go back to the other slide. Hopefully it doesn't do that again. Okay, so I was talking about, what combinations of variables that we used to evaluate where to put the mesh. And we looked at things like position, the mesh type, the resins for like what the material of construction was for the mesh, the tie resins, the composite thicknesses, and the layer thicknesses and process conditions. And from all of those, now there are a lot more data than I'm showing here, but I'm showing the abrasion, the puncture, and the tear strength performance versus 8 different candidates that we trialed. Now, again, there were many more. But what this shows is that for abrasion, puncture, and tear, we found that the addition of a nylon mesh gave us a large advantage over other candidates, and exceeded our expectations in some cases for the improvements that we could make. And you can see these three candidates here, the three in the middle, because the band here is very light, are the nylon candidates that performed quite well. So we still haven't answered the question yet, but I'll get there in a minute. So the nylon mesh required careful selection and process development for the tie layers to successfully incorporate the mesh. And so here I show how we did this evaluation. A multi-stage development plan was followed to refine the tie layer resin selection and the extrusion lamination process. So first, the Gelbo test was used to rule out film composites that formed pinholes. And really, so that was our initial experimentation. It was more broad, really looking for gross defects. Then when the experimental films no longer formed pinholes, image analysis was used to evaluate and reduce white lines that formed during Gelbo flex testing. And that helped us narrow down our selection. And then finally, a displacement test was used when we were at the limits of our image analysis test to examine and minimize haze, which correlated to interlayer adhesion. And I will review each of these stages and discuss the analytical methods and the outcome in the next few slides. To help visualize, here you can see the nylon mesh film composite. So here, right here, with the nylon embedded in the tie layer. So this is our mesh, and you can see the tie layer protruding through that mesh. And another image of a cross section with a completed mesh film composite. And so you can see the cross section here, and this is actually our tie layer, and this is our contact layer. So you can see that the mesh was placed below the gas barrier layer. So to achieve successful interlayer adhesion and maintain flexibility, the tie layer elasticity, melt flow, and compatibility needed to be taken into consideration. For the first stage of experimentation, we used 2,700 cycles on the Gelbo flex tester, and then the die test, which looked for the pinhole formation. And we used that to eliminate stiffer tie layer materials and narrow down the overall film thickness range. We then moved on to evaluating white line formation of integral film candidates. So what is a white line in the film? And there were some pictures earlier of the EVOH with those stress lines, and those were white lines. They're typically caused by stresses on the film, which can result in delamination between layers. And so you can see here with flexing that you can delaminate layers, you can show white lines. It also is showing extreme stress. Using cross-polar films, I don't know if everybody's familiar with what cross-polar films are, but they're polarized films. And so if you can imagine, there's stripes of lines, and they control the light that travels through them. So they only allow travel of the light in one direction through that film. And if you take two of the films, so stripes in north-south, and you take stripes in east-west, when you put them together, they're black. And so you can see with my glasses here that the background is black, and that's because the two films are laying over each other, and it's black. Where it's light is actually where something called birefringence happens. So you can see the image come through because the light is being bent, and you're able to see the light. Yeah, so areas of high stress do appear in here. See that on the glasses where the attachment is for the frame to the polycarbonate, you can see these bright areas, and bright areas are are caused by birefringence, and it helps us detect where there is stress on an object. So looking at our film, right, this is a post-Gelbo film sample, and it's imaged under cross-polarization. And it highlights areas of stress. And so using this cross-polar film makes it possible to quantify the degree of white lines through image analysis. So taking that initial cross-polar image, this is the process that I followed to evaluate the white lines. So first, the image is converted to black and white. Then the contrast is adjusted to remove glare that can be mistaken as a white line by the macro. So a macro is then run to binarize the image and remove the grayscale. Then another macro is run to skeletonize the binary image. And finally, a branching analysis is run. Aspects of the output, like junctions and complex junctions, which are intersections of 3 or 4 branches, correlated to the degree of white lines formed and ultimately the flexibility of the mesh film composite. And so you can see here, there are all these little lines, and where you have all these branches connecting is signifying an area of higher stress. And this process quantifies the number and the degree of those white lines. With the Gelbo Flex image analysis, we had quantifiable data that was used to narrow the process parameter. Oops, sorry, the process, getting ahead of myself. We used the data to be able to narrow the process parameter window and to refine the tie layer resin selection until the test was unable to further distinguish the differences, right? And so you can see here that we had a formulation change where we started out with a cross-polar Gelbo image that had a high degree of damage done during the Gelbo test visually. And you can see that when we had the formulation change, that we got to this place where we had a film that was much more robust to flex. But again, judging that by eye and being able to make decisions about how to move the process forward made it difficult without having the image analysis. So taking a look at the branching analysis helped us to be able to quantify the data and make the right moves forward. And so you can see how the branching analysis agrees with the visual assessment on these samples. Okay. So again, with the Gelbo Flex images, we were able to narrow that process parameter window down and refine the tie layer resin selection. And we had to stop once we were unable to further distinguish differences. And we used another method to fine tune the tie layer. And we utilized haze as this measurement, and the haze was generated by a displacement test. The displacement test is a modified puncture test where we used a blunted, so I don't have the picture of the blunted test, but we basically used this kind of pin and we created a blunted tip, and we traveled a specific distance through the film to stretch it. And then we analyzed haze to examine the interlayer adhesion. So this is an example of the film mesh composite after the displacement test. Small samples were taken from 4 locations. So you can see we took like north, south, east, west, and we measured 2 different features. We measured the distance of the haze that was generated after the test from the point of contact. So you can see where the blunted tip started to stretch the film, and that you can see the haze kind of generated through here. And we would measure the distance, and we would also measure the average haze over those those samples. So this is a series of images that shows the improvements to the film using the displacement data as feedback. We started out with poor elasticity where the film actually broke. And so you can see that here, that the displacement of this film resulted in film that was not as elastic as we had hoped it to be. And then we made formulation improvements, and we ended up attaining good elasticity, right? So no breakage, but it was still resulting in haze, and you can actually see some haze farther out. And through more process and formulation changes, we ended up with something that achieved good elasticity and lamination adhesion, where the haze was minimized after stretching. So there's barely any haze on this sample. So we really proved that we had good elasticity and good lamination adhesion with this test. So with all the work that we've done, right, now I can review what the outcome is and the performance of the new composite film. So here's a summary of the advancements made during formulating our new film called Ultimus. The film fluid contact layer is clean, cell compatible, flexible, and durable. The gas barrier layer has increased flexibility. The mesh provides enhanced abrasion and puncture resistance, and the tie layers provide flexible, robust lamination adhesion. Comparing Ultimus to 5 commercially available single-use bioprocessing films for abrasion and puncture, the data shows that the new film provides superior performance. And so we really do stand out in terms of our robustness for abrasion and puncture, being, as much as 10x and 2x more than what's on the market today. We see the same trend with tensile strength and flex crack resistance. And with flex crack resistance, our benchmark was to use 900 cycles on the Gelbo. And so you can see the competitive films that were tested here all produced holes on 900 cycles of flex testing. And we're validated to 900 cycles. However, as I discussed earlier, our benchmark was 2,700 cycles without having a hole. So this 100% is an understatement in terms of how much more flex durability our film provides. We have additional strength data that shows that a pressurized 1 liter 2D bag made with Ultimus film can withstand 25 PSI before bursting. And we directly addressed the high-risk transport of a bulk drug substance by a test that we have here shown. We used 5 1,000-liter Ultimus bags, and they were vibration tested in our collapsible bin filled with water. They were vibrated for 8 hours, simulating 2,400 miles of travel distance. There were no leaks that occurred. All the bags passed visual inspection, and they all passed a post-vibration integrity test. We also validated our 500-liter transport bin bags to withstand the rigors of ISTA 3E handling conditions without leaking. And that includes shock, so impact. And again, we have another vibration test, and there are different drops where the container gets dropped a certain distance. We actually surpassed some of this, and we went up to 4 miles an hour and dropped 8 inches, and we were still integral. So Ultimus film is targeted to be used to manufacture large volume 3D assemblies. So storage containers, single-use bins, transportation bins, and single-use mixers and bioreactors. And so our last poll is, where would you want to use Ultimus film next? So would it be in small format bags, final fill, sampling, or just everything? Get some grocery bags made out of it. All right. What does everybody think? Let's look at the poll. Wow, everything. Final fill. Great. All right, well, this actually concludes my presentation. And I want to thank you for attending and invite you to ask any questions.
Thank you very much, Shannon.
Thank you.
So hope everyone found this interesting and Shannon's examples valuable. Would you like to please post any questions on the chat, or feel free to unmute and ask Shannon directly? Does anyone have any questions? Okay, yeah, we've got. So thank you, Clinton. Clinton asked, can you comment on the type of integrity test that is performed on the new bags?
Yes. So we validated an air integrity test. It's similar to our other air integrity tests where we fill the bag with air to a certain pressure, and we look for pressure decay that indicates a leak of, I believe it's 1 to 2 microns. It's very similar to our current product specifications. We also did some other integrity tests during development that used soapy water to look for even smaller holes during our integrity testing. That was also employed during the test where we did the vibration testing and the ISTA 3E testing to ensure that the bag was integral even with smaller to smaller holes.
Hope that answered the question, Clinton.
I hope so. Thank you.
Thank you. Yep. So the comment is very interesting product.
Well, thank you.
Do we have another question? Shannon, maybe you could answer what is the most common question that you are asked normally when you're doing this presentation?
I'm not sure, really. I haven't had many questions. I think there have been questions around the methods that we've used to evaluate how we got to where we are, which is kind of why the presentation was put together. So the presentation really is answering questions that people ask me. So I think I think it's hard to say because the presentation is really in response to the questions that people ask.
Right, a good answer. Hence, you're not getting so many questions, maybe.
Right, then I don't get any questions. Right,
that
could be why we don't have a lot of questions.
Yeah. Okay, but if anyone does, otherwise we will finish the session early and let Shannon get a few bits of sleep. But if anyone does have a question, please do post it now, or forever hold your peace, or else please unmute. Just so everyone knows, this session has been recorded and it will be posted up on ISPE Singapore affiliates YouTube page. So for anyone that joined in later, and we saw a couple of people who might have missed the beginning. So if you want to catch the session again, please do go to YouTube and search under the affiliate. You'll also find some other Technical Tuesday sessions and other events that we've recorded there as well. And I see that Shannon's contact details have been posted up by Bennett. In fact, if anyone has any questions following this session, we will also forward it on to you as well and the team. So not to worry about that. Last chance for anyone to put their question in. Otherwise, we will be able to bid everyone a good night and for Shannon to be able to get on as well. Okay, we've got a thank you. So I think with that, I'd like to thank you, Shannon, for waking up
Thank you.
to share your experience with us and for your team for joining us on this session. And we thank everyone else who's in Asia and wherever they might be for joining us this evening. And we look forward to seeing you all at future sessions. So unless there's anything else, I'd like to thank everyone and wish you all a very good evening and rest of day 2.
Well, thank you, everyone.
All right. Thank you, Shannon. Take care.
All right. Thank you.
Bye-bye.
Bye.
Bye.
Bye.